Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language lecture series. Today is kind of a bittersweet moment for me. Not bitter because the theme is going to be Introduction to Integral Exponents, but rather because this wraps up our lecture series. It has been a real pleasure for me to be able to present this, and I'm hoping that it was worth your time that you invested in watching this. There's a saying in the hotel business that any room that we don't rent today never gets rented, because tomorrow it's tomorrow's room. And I feel the same way about the use of time. Any hour that we waste today can't be recuperated tomorrow, because tomorrow it counts as tomorrow's quota. So all we can hope for when we spend time together is that the time was worthwhile being spent that way. I know it was that way at my end. I hope it was that way at your end. And with that as an introduction, let's get into why it's important to understand the structure of exponents as much from an algebraic point of view, and maybe even more so from an algebraic point of view than it was from an arithmetic point of view. You see, when you're dealing with arithmetic, you have specific numbers. Whenever I see 4 plus 3, I can replace it by 7. If I have x plus y, what do I replace that by? I don't know what the value of x is going to be chosen to be. I don't know what the value of y is going to be chosen to be. So basically, things that we can sort of visualize in arithmetic have to be formulated in a way that people can see how they would apply algebraically. Let me see if I can give you an example. Suppose I have 2 to the third times 2 to the second power. And I know the definition of exponents. I know that 2 to the third means the product of 3 2's. And 2 to the second means the product of 2 2's. So it's the product of 3 2's times the product of 2 2's, okay? But I also know that 2 times 2 times 2 is 8, and that 2 times 2 is 4. So I also know that this is 8 times 4, and I know that 8 times 4 is 32. So yeah, I could do this. I could say, okay, I'm going to multiply 3 factors of 2 by 2 factors of 2. By associativity, I don't need the parentheses here. And altogether, I have 5 factors of 2. But you might say, why would I do this when it's so easy to get 32? Well, the answer is in algebra, you don't see numbers like 2. You might see an x, you might see a y, you might see b, c, whatever the symbol happens to be. What are you going to do with x to the third times x to the second? Notice I use a dot here for multiplication, because the multiplication symbol, the time sign, looks too much like an X. That's another reason why people use a dot. Sometimes they just enclose things in parentheses. Doesn't really matter. But now I know what? By the basic definition, I have 3 factors of X multiplied by 2 more factors of X. By the associative property, I can group all these 5 together. So I have a product of 5 factors of x, and that's x to the 5th power. You see, here I had a choice between writing 32 and writing 2 to the 5th power. Here, I had to know how do you combine 2 exponents when you're multiplying 2 numbers where the bases are the same, but the exponent is different. And here you have to be very, very careful. Do you remember when we were doing fractions, we mentioned that when you learn fractions mechanically and you don't realize that the 7 is really the noun, meaning that this is 3 7s plus 2 7s, which should be 5 7s, that kids will look at this, they see the plus sign, and so they add everything in sight. And let me cross that out, so nobody watching this will think I thought that was the right answer, is that when you say 3 7s plus 2 7s and spell out the word 7s, people see that the answer is 5 7s, not 5 14ths. But when you're doing things mechanically and have no idea what the answer is supposed to mean, that's when you say things like 5 14ths. Well, the same thing happens when I see 2 to the 4th plus 2 to the 3rd power, okay? I can see a student saying, oh, you're adding here. So the 2 and 2 gives me 4, and the 4 plus 3 gives me 7. That looks okay to me. And kids say, professor might mark it wrong, but I don't see anything wrong with this. I mean, 2 plus 2 is 4, and 4 plus 3 is 7. Where's my mistake? Your mistake isn't in the arithmetic, it's in how you combine the steps. In other words, you don't do the problem this way, and let's see why. When in doubt, go back to the basic definition. See, let's look at 2 to the 4th plus 2 to the 3rd and see what that really says. It's 2 times 2 times 2 times 2 plus 2 times 2 times 2. Well, 2 times 2 times 2 times 2 is 16. 2 times 2 times 2 is 8. But what are you doing? You're not multiplying the 8 by the 16. You're adding them. The answer is 24. Even though if you look at this, there doesn't seem to be any resemblance between the answer and what these numbers look like, except by coincidence, 2 to the 4th power looks a little bit like 24 if you write it sloppily. But the point was what? As you're looking at this, you see you don't have a string just of multiplications. There's a plus sign interrupting that. And by the way, as far as 4 to the 7th is concerned, 4 to the 7th is the product of 7 factors of 4. I did that on my calculator rather than to multiply it all out. That's 16,384. There's no way that 16,384 is the same as 24. But what you might have noticed was, hey, if this had been a time sign instead of a plus sign, I could have done this, because now with the time sign down here, I have a string. 4 factors of 2 times 3 more factors of 2, that's 7 factors of 2 altogether. So now I can make up a shortcut. I can say, oh, look at, when I have 2 to the 4th times 2 to the 3rd, I have 4 factors of 2 multiplied by 3 factors of 2. That gives me altogether 4 plus 3, or 7 factors of 2. In other words, now that I see the answer over here, I see, look what happened. The 2 was the base here, it's still the base here. 4 and 3 were the exponents here. 4 plus 3 is the exponent over here. So based on this, because I could have put any number in here and the same logic would have followed. If I put a 7 in here, just replace all the 2's by 7's down here, same result holds. If I put a 15 in here, same results hold. So the first property we have, the first rule for multiplying like bases. Like basis means you're multiplying 2 numbers where the bases are the same, but the exponents might be different. And the way we state that mathematically to cover all these cases at once, and notice how ominous this can be if you're memorizing, if m and n are positive integers, and if b denotes any base, then b raised to the nth power times b raised to the mth power is b raised to the n plus m power. And so what that means is, mechanically, if you give me numbers to substitute in here, suppose I decide to replace n by 20 and m by 30, the problem becomes what? 2 to the 20th times 2 to the 30th is 2 to the 20 plus 30, or 2 to the 50th. Okay? Now, I can do this blindly. It doesn't matter. I get the right answer here. Okay? But it doesn't really tell me exactly what's going on over here. In fact, 2 to the 50th, imagine what this would be trying to write this out longhand, 2 to the 50th power. I did it on my calculator, and what did it come out to be? Units, thousands, millions, billions, trillions, quadrillion. This is over a quadrillion, way, over 1,000 trillions. This is a huge number. So suppose you were to flip a coin 50 times, okay? The number of possible outcomes would be this huge number. And you can see how quickly this stuff requires a calculator and the like. Now, here we could do this, but what if it was x to the 20th times x to the 30th? You would still add the exponents. What you're saying mentally is, I have 20 factors of x multiplied by 30 more factors of x, so that will give me 50 factors of x altogether. Okay? So that's one of our rules. Okay? By the way, this comes in sort of handy when you're using scientific notation. In other words, notice that in place value notation, okay, 10,000 would be 10 to the 4th power, 1,000 would be 10 to the 3rd power, 100 would be 10 to the 2nd power, okay, 10 would be 10 to the 1st power. Notice what's happening. As you go from one row to the next, you're dividing by 10 each time, and in the second column, you're reducing the exponent by 1 each time. So if we kept doing that, what would happen? See, 10 divided by 1,000, by 10,000 is 1,000. 1,000 divided by 10 is 100. 100 divided by 10 is 10. 10 divided by 10 would be 1. 1 divided by 10 would be 1/10. 1/10 divided by 10 is 1/10 of 1/10. That's 1/100th. And if you divided this by 10, it would become 1/1000th. Meanwhile, what's happening over here? The exponents are decreasing by 1 each time. 4, 3, 2, 1, 0, -1, -2, -3. And what we start to notice over here is that the exponent tells you the number of zeros that are going to follow the 1. And if you'll notice that the negative exponent simply gives you the reciprocal of the positive exponent. In other words, 10 to the -3 was 1 over 1,000, but 10 to the third was 1,000. 10 to the -2 was 1 over 100, but 10 to the second power was 100. And so now we have a rule, at least for 10. 10 to the nth power is a 1 followed, for any positive integer n, 10 to the nth power is a 1 followed by n zeros. 10 to the 0 was 1, and 10 to the -n was the reciprocal of 10 to the n. This is very nice for tens, but a logical question could be, well, what happens if instead of 10 you just had any base b? What would happen here if we replace 10 by b? And we'll do that momentarily to show you how that works. But I thought you'd like to see how what we've done just by using tens is very effective. Very often in mathematics you encounter products that are quite huge. I'll read this number once. It's 3,167,237,267 times 2,456,098. And you have to tackle this problem. Well, watch what happens with scientific notation. It's easy to estimate products of single digits. If I wanted the decimal point over here, I would have to move the decimal point 9 places to the left. So to offset that, if I start with the decimal point 9 places to the left, I would have to multiply that by 10 to the 9th power. See, every time you multiply by 10, you're moving the decimal point 1 place to the right. So in other words, if I move the decimal point 9 places to the right over here, I get this number. Over here, to get a number that's between 1 and 10, I have to move the decimal point 6 places. So to move it back, I have to also move it 10 to the 6th power. Now what happens? I'm multiplying a number that's close to 3 by a number that's close to 2.5 times 10 to the 9th times 10 to the 6th. The rule for adding exponents when you're multiplying like bases is you just add the exponents. And so what we get is this number here, which is pretty close. That's why I write the squiggly equal sign. This is pretty close to 7.5. See, it's 3 times 2.5. And what's the power of 10? 9 plus 6 is 15. This is basically a 16-digit number. This is a number that's bigger than 10 to the 15th, but smaller than 10 to the 16th. When you're memorizing, all kinds of crazy things can happen. For example, there's a tendency to confuse 2 to the 3rd times 2 to the 4th with 3 to the 2nd times 4 to the 2nd. What's the difference between these problems? All I did was interchange the exponent with the base. Now, to see what's happening over here, all I have to do is go back to the basic definition. I don't know what the rule is going to be. I'm just going to go back to the basic definition. 3 squared is 3 times 3. 4 squared is 4 times 4. But I notice that I can rearrange terms any way that I want. To get the 3 times 4 to be displayed more prominently, I'll just interchange this 4 with the 3 over here. And what do we have over here? This is the same as 3 times 4. See, 3 times 4 times 3 times 4. That's 3 times 4 to the 2nd power. And it kind of looks like all we did was we looked at this part without the exponents and just put the exponent outside. Okay? And this might lead us to what the general rule might be. Here we're not multiplying like bases, we're multiplying like exponents. If b and c are any numbers, and n is any positive integer, b to the n times c to the n is what? Pretend the n's aren't here. that's b times c, and then raise the whole thing to the nth power. Notice, by the way, how different this was when we had the base being the same and the exponents being different. In this case, what did we do? We kept the base the same and we added the exponents. Can you begin to see how complicated this is if you were relying on memory, how easy it would be to confuse all these things? Let's just do another problem type here. Is there a time when you multiply exponents? Well, let's suppose I asked you what would happen if you took 3 to the second power and raised that to the third power. Well, what does the third power mean? It means everything that it's modifying, that's the number of times you're going to multiply what's inside the parentheses. In other words, this says what? We want 3 factors of 3 squared. In other words, this is going to stand for what? 3 to the second power plus 3 to the second power plus 3 to the second power. That's going to be the same as what? 2 factors of 3 plus 2 more factors of 3 plus 2 more factors of 3. That's 6 factors of 3. Or you can write it out this way and actually count them. 3 squared is 3 times 3, 3 times 3, 3 times 3, 3 to the 6th power. So what's rule number 3? Raising a power to a power. If b is any base and m and n are any positive integers, then b to the mth power raised to the nth power is just b to the m times n power. And again, you can memorize these things, or you can do what? Always go back to the basic definition. Now, we talked about 10 to the 0 being 1 before. What if b is any base? What would b to the 0 be? Well, again, this almost immediately when you replace a number by b, people think of algebra and it gets scarier. To make it easier to visualize, let's suppose b was equal to 3, okay? And let's take 3 to the 4th multiplied by 3 to the 0. I haven't defined 3 to the 0 yet. Up until now, the exponents are only defined for positive whole numbers. 0 is not positive. It's neither positive nor negative, okay? So I'm free to make up 3 to the 0 to be whatever I want it to be. But let me see what happens if I want the rule for like bases to still hold. See, what does 3 to the 4th times 3 to the 0 tell me if I want the rule that b to the n times b to the m is b to the n plus m? This would be 3 raised to the 4 plus 0 power, but 4 plus 0 is 4, so this would still be 3 to the 4th. What number do I multiply 3 to the 4th by to get 3 to the 4th? 1. Another way of seeing that is if I look at this and I look at this, I can just cancel the 3 to the 4th and get that 3 to the 0 equals 1. Now, I don't have to do that. It's just that I like that rule so much that I want to make sure that whatever else I do, I don't violate that rule. For example, I could have said, hey, I want 3 to the 0 to be 0. Fine. What would happen then? I still want this rule to be true. This would say that 3 to the 4th times 3 to the 0 still has to be 3 to the 4th. But if 3 to the 0 is 0, any number times 0 is 0, and therefore this rule would be incorrect. So it's not that I can't define b to the 0 to be 0, it's that I don't get what I want to maintain about structure if I do it that way. Same with negative exponents, and I'm going through this briefly because, again, these are done more extensively in our PowerPoints and the like, but I just want you to see how much there is to memorize if you don't rely on logic. I want to define this. I know that negative 3 and 3 add up to 0, so I say, okay, 2 to the 3rd power times 2 to the negative 3 would be 2 to the 3 plus negative 3. That's 2 to the 0 because 3 plus negative 3 is 0. We just saw that any number raised to the 0 power is 1. So 2 to the negative 3 must be the reciprocal of 2 to the 3rd. In other words, just divide both sides by 2 to the 3rd here. 2 to the negative 3 is 1 over 2 to the 3rd. Replace the 2 by b. So in other words, b to the negative n is the reciprocal of b to the n. b to the negative n isn't a negative number. It just means 1 divided by b. And our final practice problem of our course is what whole number is named by 2 to the 3rd times 2 to the negative 4 times 2 to the negative 1 raised to the negative 1 power times 3 squared. Pause the video, work out the problem, and then come back and see our solution. And we're just going to do the solution mechanically just to show you how many rules are involved here, okay? Let's do this problem just by using the rules for exponents that we already talked about. The problem was what? 2 to the third times 2 to the negative 4 times 2 to the negative 1 raised to the negative 1 power times 3 squared. Okay? 2 to the negative 1 to the negative 1. Remember, our rule was what? To multiply, to raise a power to a power, we multiply the two exponents. We know that negative 1 times negative 1 is positive 1. This becomes 2 to the fourth times 2 to the negative 4, 2 to the third times 2 to the negative fourth times 2 to the first equal times 3 squared. These are like base, so we can add the exponents. 3 plus negative 4 plus 1 times 3 squared. 3 plus negative 4 is negative 1 plus 1 is 0. So this can be replaced by 2 to the 0. This is 3 squared. 2 to the 0 is 1. 1 times 3 squared is 9. So the answer to this problem, after all this work, is 9. Okay? Now, admittedly, this has been a jam-packed computational lecture. Did a lot in a relatively little amount of time. And you can visualize how confusing this would be to a real beginner. In fact, it would probably be broken down into several lessons. But can you see how easy it would be to get these things confused if all you were doing was relying on memory? There are so many rules, things look so much alike, that if you're memorizing, it's hard to remember which is which. On the other hand, by using logic, it becomes relatively easy. Let's put it this way. By using the basic definition and just going step by step through the rules that are more natural to us, we arrive at things that are fairly complicated, but by doing them in a step-by-step manner which makes sense to us. And the more sense it makes to us, the easier it is to internalize. So let me conclude our series as one educator to fellow educators. Our main job is not to show how much math we know. It's to show how much we can teach our students. It's sort of like in sports. Great players don't always become great coaches. In fact, many of them fail miserably. And many great coaches were mediocre at best players. The mediocre player might have known the logic behind the game, but wasn't given the physical attributes to achieve it. I often wanted to make up a sweatshirt for successful coaches who were mediocre players by having a sweatshirt that said, "Ain't it amazing what you can do with your brains and somebody else's body?" Well, it's the same with us as teachers. Any math that we know comes under the players category. We learn to play math. Now our job is to communicate that to our students. And to do that, we realize that not one size fits all. So the more methods we have that can help students understand, the better the classroom atmosphere will be. In other words, you can pick out the best method that you like, and in the utopian situation, all the kids will get it. It's never worked for me. What happens is a lot of the kids get it, a lot of them don't. I'm not going to teach my students 7 different ways to do the problem. I want to know 7 different ways, so if that method doesn't work, I can try another one. I will be patient as long as I have other methods of explaining it. The time I tend to become impatient is when I've used up all of my resources and the student still doesn't get it. So in that vein, this was not a course. It was not a course to teach you math. It was not a course to tell you, give up what you're doing and do it the right way. No, this is one more tool that you can add to your toolkit in the event that it may help your students do better. And for me, it's been a distinct pleasure trying to get this message across to you. I hope you've internalized it in a way that you feel the time was beneficially spent. From my point of view, it was spent marvelously. I thank you all for bearing with me, and God bless you all. Thank you.